Hansen. I work as a consultant at Kodemaker, which is located in Oslo, Norway. When I'm not working at Kodemaker, I work in a programming language called Gren, which is a sort of spiritual successor to Elm that I've contributed to in the past. Now, in my work at Kodemaker, I've been contracted out as a full-stack developer to Lovdata, which is a foundation with the responsibility to produce and or publish the legal gazette, Norwegian statutes in force, Norwegian treaty register, and many other publications containing acts, regulations, and legislation. And they make this available for free online, but also in text, or several of them are also in physical copies if those are more interesting. Now, to fund their entire operation, they have this commercial offering called Lovdata Pro, which offers features on top of these publications, like making notes, highlights, notifications on changes, AI search, etc. And it's used by pretty much all the universities and law firms in Norway, as well as anyone else who has a reason to consult legal documents on a recurring basis. So Lovdata, that was the wrong screen. Let's see. So Lovdata Pro looks like this. So this is the Norwegian Penal Code, or straffeloven. So here you can sort of like browse through and read, but you can also make highlights if you want to, and you can also browse by your highlights or by notes made by you or anyone else in the company. So if you are a law firm that specializes in the penal code, you can all sort of collaborate on the notes and highlights and stuff. And you can add notifications either to the document as a whole or through specific subsections of the document to be kept up to date on changes in the law. There are a bunch of other features as well, but in general, this is what it looks like. Now, this specific version of Lovdata Pro is a rewrite. It was published late. It was released late last year. The previous version of Lovdata Pro was written in Google Web Toolkit, which is now end of life, and so we, or Lovdata, rewrote this in Elm. Now, there's an interesting challenge in using Elm or any virtual DOM-based technology in a documentation reader like this, and that is that some of these documents are big. The tax code specifically, fully rendered at the time that I joined the project, generated around 250,000 DOM nodes. And earlier today, I checked Aftenposten.no, which is one of Norway's largest newspapers. Their front page consisted of 1,891 DOM nodes. So this was bigger. And the result of that is that performance, especially on older devices, mobile phones, was either it crashed or it was very, very slow. And the reason really, or at least partly, lies in how the virtual DOM as a technique works. There are probably a lot of you that knows this, but this is sort of important to the stuff that we're talking about, so I'm just going to briefly go through how it works. So when you have a virtual DOM, you're going to have a function or component or whatever that is going to return a virtual representation of the DOM you want inserted into the browser. This then is converted into actual DOM, and then on subsequent renderings, the view is still going to return like the entire, this is how I want the DOM to look like. And then it's going to take the actual DOM and the virtual DOM, figure out the difference, and only add the thing that differs or remove the thing that differs. And the reason for this reconciliation is not really about performance. It's about maintaining important state, like which element is focused, where is your cursor inside this text area, and these sort of things. And of course, the upside for us developers is that we don't have to care about, we don't have to remember that when this thing updated, we also have to update this other thing. We can just say, this is how we want the thing to look like, and it's up to the framework to do that correctly. And that goes to say, and the how did this happen? And the the um, the side effect of this is, of course, that performance is largely tied to how big your virtual DOM is and how big the actual DOM is, because it has to compare these node by node. So, of course, the bigger the virtual DOM, the bigger the actual DOM, the slower this is going to go, everything else being equal. Now, Elm, in particular, makes this extra interesting. So in React, components of your view can have local state. And when the local state is updated, React can do just a comparison of this component and all its children instead of the entire virtual DOM. But in Elm, we don't have local state. In fact, we don't have side effects at all. There are no exceptions being thrown. There are no mutations happening. And so we have the application state. And when that changes, we generate all the DOM. And that's it, really. The trade-off, from a performance side, it makes things a bit interesting. But from a readability and reasonability side, it makes things very easy because you know that things are just not going to change underneath you, and things can only happen in specific cases. But for performance, especially, this made things more interesting. Now, I'm going to mention performance a lot. And I think it's important that we understand the context that I'm referring it to. As developers, we tend to use the latest devices and usually the most expensive devices in the range, whereas the people we make software for don't. They might be using a 5-year-old phone and probably not the most expensive phone at the time, and so they are not going to be able to run our programs at the same performance that we are. So in order for us to detect and improve the performance of programs, what we do is that we open up a DevTools, go into the Performance tab, and select 20x slowdown in the profiler. So when I say that the performance is too slow, it's in this context. So I expect to have a perfectly I want good performance even when I'm running a 20th of my CPU. So that's my bar for good performance. Now, when I joined Lovdata, their attempted solution to kind of deal with performance was to use a common technique known as list or table virtualization. And the general idea there is that the user can't necessarily view your entire page, so you're only going to generate the virtual DOM for the section of the page that the user can see. Right? So if something is in the viewport, you're going to render it as you would, and for everything that's outside of it, you're going to create a placeholder element with the same height and the same width as the actual elements that would be there. And this worked reasonably well, but I wasn't very thrilled about it because you're increasing complexity in many, many ways, right? So first off, since you're not actually having the entire DOM in there, built-in functionality like Control F for searching through text doesn't work, right? Because a lot of the content is missing. If you want to print out the document you're reading at, that wouldn't work either because, again, most of the stuff is missing. If you're going to programmatically scroll from one section of the page to another, you're going to have to insert the page you're scrolling to, probably also all the things in between, scroll there, and then remove all the previous entries again. And you're going to have to remember to do this every time you're doing programmatic scrolling. And of course, there's overhead to always keep track of the things that are visible to the user. And even with all this complexity, we had bad performance when scrolling, right? Because when scrolling, you're going to have to check what is visible, what is not. And then you have to run the view, generate the DOM, update the DOM. And you're going to do that many times per second. How many times? Well, that's a trade-off you're going to have to make. But if you don't do it often enough, they might hit the bottom and stop scrolling, or they might see a completely white page. So you have to do it often. But the more often you do it, the bigger the chances are that garbage collector is going to kick in or other stuff happening. So we didn't have good performance when scrolling, and I was tasked relatively quickly in improving scroll performance. But due to all this other complexity, I didn't really want to do that. Or like I wanted better performance, but like if we have to have all this complexity, like we implemented our own version of Control F to get this stuff working. And so I thought, like, can't there be some other way? So obviously the size of the virtual DOM is going to matter. The size of the actual DOM is going to matter. That comparison is going to be a big bottleneck for performance. But so is at this, like for 250,000 elements, generating that virtual DOM is also going to be a bottleneck for performance. And the number of times you need to do these comparisons are also going to be a bottleneck for performance. So, and the interesting thing is that when you're doing list virtualization, you're calling this comparison function a ton, right? And that's ultimately what led to bad performance while scrolling. It's because we're doing all this stuff while we're all like multiple times per second. And in a documentation reader, you might argue that reading the document and scrolling and navigating through the argument is probably the most important thing you do. And that's what people are going to measure performance by. So one of the first things, well, not one of the first things, but one of the things we did early on was to walk away from list virtualization. We took it out. We started rendering the entire document because then we didn't have to do any view updates while the users were scrolling or when they were navigating using this table. When using table of contents, there wouldn't be any stuff. And so as long as you didn't add any highlights or add any notes or open any menus, things were going to be much more fluid. Of course, that made a trade-off. It made the worst case worse. But I had a feeling that it would be easier to optimize those cases than to fix scrolling. Now, probably the most important optimization you can make when using a virtual DOM framework is to use laziness or memoization. And Elm has this as well. I think in React it's called use memo. And the cool thing about laziness or memoization is that not only do you skip creating the virtual DOM, you also skip the DOM comparison for those subtrees, which potentially can be quite huge. But the problem is that, the document we're looking at here, this is a recursive data structure, effectively, like it's a tree structure. And so you have to care, like, so this highlight has to be kind of like, it has to be pushed down from, let's see, first it has to be parsed into første del, down to chapter 13, down to chapter 17. And if I add another highlight, well, then the list of highlights would be different here. And so laziness would already be invalidated at this stage. And so how do you pass down these things and use laziness at the same time? That was quite difficult for me to figure out. But I realized that even in the case where, but I realized that other performance options were valid, or like we would want to make performance better in general, because in many cases, when this thing is invalidated because you've added new highlights or whatever, we still want that to be fast. So I thought, I'm going to work on these other optimizations, and I'll get back to this later on. Hopefully, I'll have a better understanding, or I'll have some insight that makes this thing easier. So the first thing to do when trying to optimize something is focus on algorithmic improvements. When the first time you write something, probably you're going to do it the most naive way, because A, you don't entirely know what it's going to end up looking like, and B, that's probably going to be the most readable code as well. Premature optimization is, after all, the root of all evil. That and sugar. So that was the first thing. Just if we're using a list, could we use a dictionary instead and improve performance that way? If we're calling a function multiple times, could we call it earlier and pass down the result to save in computation? And that did improve performance quite a bit. We also had to remove, I think they were using CSS, Elm CSS, which the equivalent in React world is style elements. and the way that works is that you can specify the CSS or the styling in line with your component, and then at runtime it will generate the CSS and remove it at the appropriate times. And that is very convenient for developers, but it also has a performance overhead that was just like we couldn't deal with it. It was too much. So we started there, and that gave us better performance, but still not enough. And then was sort of and then I had this insight where, interestingly, when you have a view function that returns a virtual DOM, you're doing a lot of logic, a lot of stuff inside that view function that you probably could have done once ahead of time. Like obviously in the documentation viewer, you're going to have a lot of things which are going to be identical from every time you call the view. But even in other single page applications, a lot of the things you see never really change. A lot of the things you see are the same unless you're navigating to another part of the app or something. So we did this thing where when we downloaded the document from the backend, we did a pre-processing step. And the goal of that pre-processing step is that everything that should be static between views, we will do the work now and then reclaim that stuff from memory in the actual view function. The goal was that the view function should be, if I have this element, then I'm going to allocate this thing directly without any logic in between. Now this is Elm code. If you haven't worked a lot with Elm, this is sort of like a discriminated union in TypeScript. And so we have a few states. So if we came across a picture or a latex formula, those things are truly static. You can't highlight them or you can't move them about. So in that case, we just generated the virtual DOM and saved it in our structure. And so later on, we would just have to unpack it. We didn't have to do any memory allocation or computation. It was all done ahead of time. And then, of course, we have text. And since text in Lovdata Pro is highlightable, that is a dynamic element. It requires some input from the user. But highlights in Lovdata Pro are defined by their distance from a title. So this highlight is defined as highlight the 10 characters, which are 11 characters from this title. So in order to be able to place highlights, we have to know what the distance from the title is here, here, and here. And so that's something, that calculation is something we do ahead of time. And then we have containers, essentially just divs containing highlightable text or pre-computed nodes. And before we allocate this container object, we check if all the children are highlightable text. No, sorry, if all the children are pre-computed nodes, then we don't allocate a container, we allocate another pre-computed node. We also have this depends on part ID. So anything that has like a menu like this, that's known as a part. You can think of it as a sub-chapter in the document. And so when we know that all the sub-elements here belongs to one single part, then we allocate that in a special container. Not every part has a menu. And so we represent the menus directly in the prep node instead of figuring out, should I do a menu here or not? And some parts end with a comment. And instead of figuring out if I should draw a comment here or not, we represent that in the preprocessed node. And so by doing this, we're moving a lot of logic from the view function itself, and we're moving it to the time where we load the document. And that saves a lot of logic, saves a lot of memory allocation. I forgot to mention here we have a list of attributes like the class, the event handler stuff. So we actually allocate those things ahead of time as well. So the view function actually does very little memory allocation, does very little processing, and that improved performance significantly. And I think at this step, we got to the point where the developers stopped noticing performance problems. So on the beefy machines, it was running fast. And on mobile devices, we still had a little bit of work to go. And of course, the next step then is to reduce the size of the virtual DOM. The obvious things to look at there is that, like, if you have a bunch of divs nested in each other due to layout, maybe you could use Flexbox, or maybe you can use CSS Grid in order to remove one of those divs. When you're operating a size of 250,000 nodes, like that's your offset, like that's your base, removing just one of these instances in code translates to 10,000 reduced nodes for such a document, right? So that was like the first step. Just go through, do I need all these nodes? Can I represent the same view in a different way? And that way you reduce compute, but also memory allocation, the memory required to represent the document. Another thing to look for, and I think this is something that I've seen in pretty much every project that I've been on for other clients as well, and that is that everyone, like, if you have SVG icons, someone is going to think that wouldn't this be really cool to represent in code? And it's definitely convenient because you can have an icon like this and you can like change the color at runtime depending on what you're trying to do. But it does become part of your virtual DOM. The framework has to reconcile this with the actual DOM. And I think, I believe that the browser is very bad at saying, here's the same SVG structure, so I'm going to cache that icon and use it every time I see this. So when we looked in the memory profiler, we actually saw that like 10 or 20% of our heap was SVG related. So we went away from this. Instead, we use a regular div, or we probably use icon or whatever, that had a CSS class that referenced an SVG icon that lives in a static location on the server. It's not as flexible for us, but it significantly reduced the amount of memory that we allocated and reduced the amount of stuff that the virtual DOM had to deal with as well. Another thing that I see commonly is things like this. So this and this is the same component, just open and closed. I don't think we do this anymore, but at some point this was animated. So when you click this, this would change to an X and things would slide in, and when you close it, it would slide out. Now, to animate the closing thing, you have to keep the DOM, the elements alive for the duration of the animation. And the simplest thing, and what I see most people do, is that they just always render those icons so that the animation will just work. Now you can attach an event listener so that when the animation stops, you can update the view again and remove those invisible nodes. The solution that we went with is that we keep like a list of the 2 previously toggled menus. And once you toggle a third menu, we remove the oldest one. Essentially remove the invisible nodes there. So with these 3 things, like just trying to simplify the structure, removing inline SVGs, and anything that's being animated closed and aren't visible anymore, we tried to remove that from the DOM. This brought us down from 250,000 nodes to 150,000 nodes. And that was the point that I submitted the talk to this conference. But since then, we've actually managed to bring it down to 115,000 nodes for the tax code. And of course, this scales with every document we have. And with every reduction, we reduce the required amount of memory that the device needs to have, and we improve the speed at which we manage to update the DOM. But it was still not fast enough. So now we got to the point where we could revisit the use of laziness. Now, since we have this depends on part ID container, it makes it very easy for us to know when we are at the bottom of the hierarchy and looking at like a single chapter of things, right? Typically, this would be like paragraph 71 here. You have a title, you have a part menu, and you have 4 or 5 text nodes, right? And that would be one depends on part ID element. So what we did was we added another pre-processing step. So when we got the data from the backend, which like here are all the highlights, here are all the notes, etc., we grouped them by the chapters or the part IDs. And so when we got to this page, we would get the relevant state from a dictionary, and then we would pass just that state to the next level. We wouldn't pass the dictionary for all the chapters, because if you were to add and highlight somewhere, that dictionary would change and that would invalidate the laziness. But at least for the parts at the lowest part of the tree would be lazy loaded in most cases. And we also realized we could do this at the top as well. So we could group all these chapter states by the top chapter. So for the penal code in particular, we will, if you make a change within Andel, we would lazy render this and we would lazy render this. And then we would also lazy render everything that isn't where the change happens. Which means that when we're updating the virtual DOM, we're actually skipping over most of it. Now, at this point, you might imagine that performance is great. And it wasn't. But the problem now isn't JavaScript, or it isn't Elm. Elm compiles to JavaScript, so that's the thing. So this part, this is a profile of some slow execution. So this part right here, this is JavaScript. This part, which is significantly longer, that's the CSS engine trying to keep up. And the reason this happens, and it's happening in one specific case, so if I click this button, which is to show the right panel here, you can see, no, you can't see that because my screen is very big. But like on a smaller screen, opening this right panel would resize the document column. And when you resize the document column, the CSS engine will realize that, oh, some text would have to take more vertical space. And that means that I have to lay out everything over again. Because if the first element takes up more vertical space, then the next element has to be positioned lower down. That might take up more space. And so the CSS engine, whenever we resize the document for whatever reason, it would, like for large documents, the CSS engine would just spend a lot of time figuring out the layout. And that was a hard time for me. So I spent all this time trying to make the code fast. I make the code fast, and now the CSS can't keep up. And if you try to Google, how do I improve the CSS performance, you won't find anything, or you would find one link, because no one has an issue with CSS performance. Fortunately, there is a CSS property that can help. And this is now available and correctly implemented in all major browsers. I think this was introduced in all major browsers last year, but Safari had this critical bug. It always has, yeah. But now it works. So now you can use it. And that's content visibility auto. And what content visibility auto does is that you're essentially telling the CSS engine that I don't care about the correct layout or the correct styling with this if the user can't see it. So when you add this to the, so I think we've added this to the main chapters and the direct subchapters. Whoop. And so that's like, so, yeah, I can't, can I? No, that would, no. All right. Well, anyway, that ends up actually giving us great performance because when we resize, it's not going to bother calculating what's above the screen or below it. It only calculates the things you've seen, which is pretty fast. The trade-off, though, is that this scrolling indicator is going to lie to you, right? Because it doesn't know the actual height of the document. So as you're scrolling, that thing is going to jump around and change sizes on you. But that's the trade-off we've had to make for good performance. And of course, due to the size of the document, this is not a virtual DOM related issue either. This is the way of having great performance with documents this big. Another thing to keep in mind is that if you're calling certain JavaScript function that relies on correct positioning, like get client offset, I believe it's called. If you do that, then it has to calculate everything, and this property won't help you. But for our use case, as long as we stay a bit careful, it works wonders for us. And content visibility auto is like, it only works at the CSS level, so it doesn't affect Control F or Control P or whatever. So yeah. And with that, with all those things, we now have, even with 20x slowdown, we have a app that works with very good performance across all the devices that I've tested. And that's it, really. So I will try to be at the speaker's corner in the next 20 minutes or so. So if you have any questions about the techniques here, or Gren, or Elm, or Lovdata, or Kodemaker, come find me. Thank you.